Okay, in this video we're going to look at a simple max-min problem, and what we have here is not a function. You'll notice that we have some y squareds in here and some x squared, so it turns out it doesn't pass the test for a true function, but that doesn't mean that we can't find maxes and mins of this graph if we were to graph it. Well, if you look carefully enough, you might recognize that, and it turns out that this thing is an ellipse. Now, I'm not going to actually complete the square and go through this whole process here. I will let that be for perhaps a pre-calc video on conics. But if we were to do this, we would get the following. We would get the following equation of an ellipse in standard form. Okay, this would be a 4, and this would be 1. You don't really need to write that one, but it helps some people. Okay, so why did I do that? Why did I put this in standard form? Well, sometimes it helps to get a visual of what's going on, just to kind of give you a vantage point, to help you see where you're going. So if you consider that we're really working with an ellipse, then maybe you can just kind of visually see what the maxes and mins should be. Okay, so if I plotted this very quickly, the center is going to be at 1, positive 2. And if you think back to your study in conics, if you take the square root of that, that gives you your a value. And that will be 2. Take the square root of this gives you your b value. I think those are conventional variables. I think most everybody uses a and b. Maybe I'm wrong. But what these tell you is they tell you how far away from the center to travel. And since the a is underneath the x variable, that's going to tell me to travel 2 units to the right and 2 units to the left. And this defines my major axis. Okay, this tells me how far to travel vertically. And so I go up 1 and I go down 1, and then the ellipse is going to look something like this. It's supposed to go through those points, but hopefully you'll forgive me for that horrible drawing. But if you look at this real quickly and just think back to what we're actually trying to find, we're trying to find maxes and mins. We're trying to find the highest point of the graph and the lowest point of the graph. Well, that looks like the highest point, and that looks like the ordered pair 1, 3. This guy right here looks like the lowest point, and he looks like the ordered pair 1, 1. Okay, so if we were just using some algebra 2, maybe some little bit of pre-calc, if you learned this in pre-calc, we could find those maxes and mins fairly easily. Okay, but how do we do it using calculus? Well, we do it the same way you find maxes and mins of any problem, and that is you have to differentiate it. So what I'm going to do is I'm going to differentiate this entire equation. I'm going to differentiate it with respect to x. Okay, now you need to be a little careful here because we have some y squareds involved. This is not a function written explicitly in terms of x. It's actually an implicit function, so we have to use implicit differentiation. Okay, so how do you differentiate this with respect to x? Well, all the x's are easy enough. What's the derivative of x squared with respect to x? And it is just 2x. So we write 2x. But implicit differentiation tells me that in order to take the derivative of 4y squared with respect to x, I first have to take the derivative of it with respect to y, and that will be 8y. Okay, but then the chain rule kicks in, because really there's a bunch of little x's that live inside of this y, and I really have another function inside of this y. I just don't know what it looks like. But that function has x's in it. So the chain rule says take the derivative of your outside function multiplied by the derivative of your inside function. Well, the derivative of the inside function is just a y prime. Minus the derivative of negative 2x is negative 2. And be careful again because you have some more y's to deal with. So the derivative of the outside function here is negative 16 multiplied by the derivative of the inside function, which is y. The derivative of 13 is 0, and the derivative of 0 is 0. So we just say equals 0. Okay, so we've differentiated it, and now what we need to do is gather up. We need to gather up our y primes on one side and everything else to the other side. So I gather up those guys, and at the same time I'm going to factor a y prime out, and I'm left with 8y minus 16. The other thing I'm going to do is I'm going to take the 2x and the negative 2 and move them to the other side, and I get 2 minus 2x. And the last thing to do is to divide by 8y minus 16, and that equals 2 minus 2x over 8y minus 16. Okay, there you go. There's your derivative. Now, what do we do with the derivative? Well, we want to know where is that derivative equal to 0? Well, it's equal to 0 right here. And that's a horrible line, and you're equal to 0 right about there. Okay, so where do those live? Well, from the algebra we know that x equals 1. So if we set this derivative equal to 0, we say 0 equals 2 minus 2x. Really, that's all I really need to do. Think about it. If y prime is 0, I could multiply both sides by 8y minus 16, and this just goes away. So it suffices to just set your numerator equal to 0, and it turns out if you solve that, you get x equals 1. Okay, but that's just one critical point. This x equals 1 gives me a 0 derivative, and most likely this is going to be the points that we're interested in. But to be thorough, let's say we didn't have this picture. Let's say we didn't know that this was an ellipse. Remember, the critical points come in two forms: either where they cause your derivative to be 0 or undefined. Okay, so let's go ahead and figure out where's this derivative undefined. And if you just look at the denominator, if y is positive 2, you could set that equal to 0 if you wanted to. But if y is a positive 2, then we get 0 in the denominator. So this is actually going to be a critical point as well. So let's get the full critical points. Let's see where these actually live. If x is equal to 1, what are my y values? Okay, and to find that, I'm going to use my standard form of the ellipse right here, and I'm just going to substitute 1 in for x. If I do that, you'll see that this whole thing goes away, and I am left with y minus 2 squared equals 1. Now this isn't too difficult to solve. Take the square root of both sides, and I get y minus 2 equals plus or minus 1. If I add 2 to the other side, I get y equals 2 plus 1, which is 3, and y equals 2 minus 1, which is 1. So when I substitute 1 in for x, I get back two values of y. Okay, let me get some more room here. I wanted to try to make this all on just one page, but that's not going to happen. So it turns out two of my critical points are when x is 1, y is 1. There's one critical point. And the other critical point is going to occur when x is 1 and y is 3. Okay, but there's two other critical points out there, and they come from this guy right here. And I'm going to do the same thing. I'm going to substitute y equals 2 in for y in this equation, and I'm going to try to figure out what x is. So let's substitute. I guess I'll do that right under here. We get x minus 1 squared divided by 4 equals 1. Now multiply both sides by 4, and you get x minus 1 squared equals 4. Take the square root of both sides, and you get x minus 1 equals plus or minus 2. And now add 1 to both sides, and you get x is equal to, well, 1 plus 2 is 3. 1 plus 2 is 3, and 1 minus 2 is negative 1. Okay, so our other two critical points then. We have an x value of 3. I got that from right here. That gives us a y value of 2. And the other one is when your x value is negative 1. And that happens when y is 2 as well. So now if we scroll back up to the page, it's really easy to see which are the maxes and which are the mins. Clearly 1, 3 was our max and 1, 1 is our minimum. But look at this. We have two other critical points, and you'll notice that your derivative is undefined there. That's an undefined slope, and that actually came up in our analysis. Okay, so we have these vertical tangent lines that occur at 3, 2 and at negative 1, 2. So there you have it. You have we have found the max and the min of this ellipse using some implicit differentiation and a little bit of algebra. So hope that made sense. We'll see you around.